Hello friend, welcome back after the long time on my channel. It's a Crew Alike Tech. Today we see the RLC series circuit. So let us see. Here is the RLC series circuit. The pure R, pure L and the pure capacitor is there. The current through the circuit is the I. The voltage drop across the resistance, this is the VR. Voltage drop across the inductor, that is the VL, and the voltage drop across the capacitor is the VC. So by adding VR, VL and VC, you able to find the voltage, that is the supplied voltage. Okay, so here is the circuit consist. This is already just we talk about that. This is the R, L and C, and this is the series circuit. That's why it's calling the RLC series circuit. So in series only the single current is there, and the voltage drop across the different components that depends upon their resistance and the reactance. So it's here the voltage drop across the resistance, that is the VR, and VR equal to I into R. This is the resistance. Okay, so this is for the pure resistance. So there is no phase difference between the current and the voltage. In second one, this is the VL, and the VL equal to I into XL. You know that the XL, that is the inductive reactance. In case of inductive reactance, the current is leading by 90. And the third case, this is the VC, and VC equal to I into XC. So this is the capacitive reactance. Okay, so according to the KVL, Kirchhoff voltage law, VR plus VL plus VC equal to V. You know very well that. So suppose if we take current as a reference, because in the circuit only the single current, one current I is there. So if you take current as a reference, then the VL leads the current by the 90 degree. VL is ahead of current, because in inductive circuit the current is lagging, that's why the VL is leading. Same as the VC lags the current by 90 degree. You know very well that for the capacitive circuit the current is leading, so the voltage is lagging. Okay, so VC and VL both are in opposite direction. Hence the circuit can either be effective inductive or the capacitive, that's depend upon the voltage drop VC and VL. Suppose the VC is larger, then the capacitive effect is more, and the VL is larger, then the inductive effect is more. So let us see. There are three possible cases in the series circuit, RLC series circuit. The first one is the VL greater than VC. So for that the XL is greater than the XC, because XL is greater than XC, that's time the drop across the inductor is increased, that's why the VL greater than the VC. Another case, in this case the XC is larger. X is larger than the voltage drop across the capacitor is larger than the voltage drop across the inductor. Okay, and the last case, that is the VL equal to EC. In this case the XL equal to XC. This is the series resonance case, that we see later in the next video. Okay, so let us see the first case, that is the VL greater than VC, or you can say that XL greater than XC, or the inductive reactance is larger than the capacitive reactance. This is the diagram. Here's the diagram. This is the total VC, sorry, VL, and this one is the VC. So the VC is deducted from the VL, so the remaining part is OC, that is the VL minus VC. Okay, so just we put VL minus VC over here, and this is the VR. By adding VR plus VL minus VC, just you found the resultant OB, that is the resultant voltage. Okay, that is V. Okay, so the current to the circuit, that is on the same phase with the resistance resistive drop, that is the VR and I on the same phase. Okay, that's already written over here. Because the VL is larger, so it's deducted VC from the VL. That part is larger. Okay, so from the diagram, what can you write? It's a triangular, that's why you can directly take the square addition and the square root gives the result. Okay, so here is the voltage and here is the current. So if you divide voltage by the impedance, then you will get current. So here is the impedance. What is the impedance? Impedance Z equal to R square plus XL minus XC square. Okay, so this is the impedance Z in case of RLC circuit and the XL greater than XC. So finally you can write directly impedance Z equal to V by I, or if you want to say what is the V, then V equal to IZ. If the length of each side of the voltage triangle is divided by the current, the impedance triangle is obtained. And that's very easy because you know that the V equal to IZ. So if you divide by the I here, you can see, then you will get the impedance triangle. So that's obtained and it's very easy. You can see here is the R, so that is the I into R, that is divided by R, that is also divided by R, and the same is this is divided by the I. So the all three sides divide by I. So instead of drop, you can find the R, reactance X and impedance Z. So this is the impedance triangle. Same as from the impedance triangle, if you want to find the power factor, then the power factor cos phi equal to R by Z. You can directly say for the cos phi, this is the nearer side and this is the hypotenuse. Okay, so cos phi equal to R by Z. This is the value of Z that is already derived previously. So if you want to find the sin phi, just you have to divide this side AB divided by the OB. Okay, so that is derived. Next, the power consumed in the circuit. What is the power consumed? So you know very well that the power P equal to VI cos phi, and instead of cos phi you can directly put down the value R by Z. So just if you put the value of V, this is the V equal to IZ, so there is no change in the current I, and instead of cos phi just we put down the value R by Z. So what is the power? That is the I square R. That is the power consumed in the circuit. So the current lags the applied voltage, the phase angle phi is negative. You know that. Okay, let's talk about the second case. VL less than the VC. So in this case, the X is larger than the XL. So here is in the first case the triangle on the top side, in this case the triangle in the bottom side, because the VL is smaller and the VC, this is the total VC. So if you deduct this value VL here, this one is the VL, from the total VC, you will find the VC minus VL. Just we put down this by, you can directly make the vector addition. This is the phasor diagram. So here is the again VR, this is the VC minus VL, and the resultant voltage V. Okay, so same thing you are able to find from the triangle. Here is the, this is the arithmetic sum. So here is the VC minus VL. So just you have to put down XC minus XL. This is the impedance triangle. So if you divide the phasor diagram by of the job by the current I, you will able to find the impedance triangle. So next, from the phasor diagram, what can you write? So you can write the impedance Z. So this is the impedance. Already derived the value of voltage V, and the divide voltage V by the impedance Z, you will find the I. So in this equation, this is the V, this is the V again, this is the V, this I is taken out, and the I equal to V by this value. So the I equal to V by Z. So you can say this is value contain the impedance. Okay, so Z equal to square root of R square plus XC minus XL, because the XC is larger. Okay, so this is the positive value, because also here the square is there. So the impedance Z equal to V by I, and you can directly say that the V equal to IZ. So again, from the impedance triangle, what is the power factor? The power factor is given by R by Z. You can directly say, already we already seen in the previous case. So the power factor cos phi equal to R divided by square root of R square plus XC minus XL. You know that the XC is larger than the XL. So the sin phi you can directly write, and the tan phi. Okay, so by inversing the value of tan, just you are able to find what is the phi. So here is the power consumed again, same as the previous case, that is the phi equal to I square. The current, let's say applied voltage, the phase angle is positive. In previous case the phi is negative, in this case the phi is positive, because the capacitive drop is larger and the capacitive current is leading the voltage. You know well that. So finally you can say what is the current in the case 1. Because the phi is negative, that's why the current I equal to Im sin omega t minus phi. And in second case, I equal to Im sin omega t plus phi. You know that the power factor is lagging. And in third case, you know that we'll see in the next video, this case especially for the resonance and series circuit. This is the XL equal to XC. There is no phase difference between the voltage and current. That's why that is the basic equation I equal to Im sin omega t. So thank you very much. If you have any question, then you can directly ask by putting your question in the comment box, and you can subscribe my channel just by searching Grow Lecture in the YouTube, and just click on the subscribe button. So thank you very much. This is up to now. So thank you very much for watching my video.